Okay, so welcome to Nuclear Video 2. We're going to do half-life today. Important that we're going to go to our reference table, or I'm sorry, our packet page 7, and then we're going to go to our reference table. We want to look at table N. So reference table N and our packet page 7. Remember that we're in the second half of our packet, our nuclear section. So here's my table N. What I'm going to focus on today with table N is this section that's going to tell me my half-life. Remember, you did half-life in earth science, so we'll continue it here. So table N is going to be our big one, but remember table O as well. They're on two different pages, but on this slide I have them together. So your page 7 should look familiar. You have your types of transmutation on top. You have your natural transmutation, which was on table N. Also, is why we use that to kind of grab our decay mode, and then we had our artificial transmutation, which remember that's got to have at least 2 reactants because I have to actually hit something or bombard something with another particle. So I'm down to half-life. So hopefully you remember some of this. You want to remember that something's half-life helps us be able to tell how old something is. And we know that radioactive substances will decay at a constant rate. So that rate that something decays will be constant. That's why I can use table N. Table N is going to give me both my half-lives, but it also is going to give you your decay modes, which is important. So there used to be an equation that they would use. Oh, I should have also told you, if you don't have a calculator at this point, please grab one. You do need a calculator. So there used to be an equation to be able to do fraction remaining that used to be on the reference tables. It's not there anymore. But to calculate my fraction remaining, I just am always going to do 1/2 raised to the n, where that n is going to represent our number of half-lives. So n is our number of half-lives. So our fraction remaining, oops, sorry, that should actually be written right down here. Slide it. Sorry. So that's how I get my fraction remaining. We're going to do it via an example of if I wanted to know the fraction remaining after 3 half-lives. So if I want to do the fraction remaining after 3 half-lives, I would just go ahead and say, okay, 1/2 raised to the 3. I would plug that into my calculator, which I could do, but sometimes when I plug it in my calculator, I leave room for error. So if it's 1/2 cubed, well, then it's really 1/2 times 1/2 times 1/2. It's 1/2 3 times. So remember, as you go across a fraction, you just multiply across the numerator, then across the denominator. So I would get 1 times 1 times 1 is 1. 2 times 2 is 4. 4 times 2 is 8. So I actually get 1/8. And that is the fraction remaining after 3 half-lives. So that means after whatever time the half-life is, after I've gone through 3 of them, I will have 1/8 of my original sample. If they ask me for my fraction remaining after 5 half-lives, well then I again could just go 1/2 raised to the 5, but remember on the Regents, you're not going to have your graphing calculator. You might be stuck with just a single 4 function. That means I won't be able to plug that in. So I would go 1/2 times 1/2 times 1/2 times 1/2 times 1/2. Count 1, 2, 3, 4, 5 halves. So again, I multiply across the ones. I get 1. And then I go across the bottom. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. So after 5 half-lives, I will have 1/32 of my original sample. It's good to know that I'm never going to, based on my half-life when I decay, I'm always going to have part of my sample remaining. I'm never going to go to 0. I'll just have infinitely small amounts of it. So that's one way that our half-lives go. They ask us for the fraction remaining. They also might ask us to find maybe our number of half-lives. So if I have to go through a problem like this, let me change my color. So I'm finding my number. Let's just go through an example. So it says if you started with a 30-gram sample of carbon-14, how much will remain after 11,460 years? So what I would do is I would go to my table N for this, and I would say, well, they told me it was carbon-14. Let's figure out what the half-life actually is. So carbon-14 is right here. I see that it does a beta decay, and its half-life is 5,715 years. So carbon-14, 5,715 years. That is its half-life. Okay, that's its half-life. So to go through and basically degrade by half, it would take that long. So they want to know, well, it's actually going to go for 11,460 years. So what I should do is figure out, well, how many half-lives is that? Take your 11,460, divide that by 5,715. What I'm doing is I'm figuring out how many half-lives. If I plug that into my calculator, I'm going to get that that is 2 half-lives. So I'm not done with the problem, but that helps me. 2 half-lives. So I started, it said, with a 30-gram sample. So I started with 30. So I'm going to say, okay, I started with 30, and then I'm going to cut it in half. So I have 15. That would be 1 half-life. Now I go through a second half-life, and I cut that in half. Half of 15 would be 7.5. That means if I started with 30 grams of my sample that had carbon-14 in it, I would have 7.5 grams left of it after 11,460 years, because each half-life was 5,715 years. That's also important that I'm introducing you to me drawing my arrows. A lot of times I like to draw arrows to represent, that's my half-life. So I'm basically drawing an arrow to kind of show, well, I went through 1, now I went through 2. Let's flip over to the very next page. So we're going to kind of continue this. So then this is actually a continuation of the very last problem. This is on page 8. And so it says, well, now what's my fraction remaining? Well, I went through 2 half-lives. So it's 1/2 raised to the 2, which is the same as going 1/2 times 1/2. So if I have 7.5 grams left, I actually have 1/4 of my sample that is remaining. Okay, so let's try another problem. It says if 60 grams of a radioisotope decays to 15 grams in 30 minutes, what is the element's half-life in minutes? So this time they don't tell me who it is, they just want to know what is the half-life. So I started with 60 grams and I decayed to 15. So let's think about it like this. I started with 60 and let's cut it in half. So I go to 60 to 30. That's not the same as 15. Let's cut 30 in half. 15. Okay. I go from 60 to 15 by cutting it in half twice. That's 1 half-life, that's 2 half-lives. So that means 30 minutes it took me to go through a half-life. So, or 2 half-lives. So I go 30 divided by 2, and I'm going to get 15. It's a time, so it's 15 minutes. Each half-life must take 15 minutes if I'm going to go from 60 to 15 in a total of 30 minutes. So the tricky thing about half-life is it's different for each problem. It's like a puzzle. You got to figure it out. Half-life means half of it is remaining. I continue to cut it, so it goes a half, a quarter, an eighth, things like that. I might have to figure out how long the half-life is. I might have to do the fraction that's remaining. I might have to do finding, like, well, what element it is if I can figure out what the half-life is. So it's hard for me to give you notes on this, basically. So what I want to do is kind of put a little bit of our examples in practice in. So I want to go to page 17 to 19 because we need to do some examples in practice. And then tonight, you won't have any other homework to practice tonight, but we will continue this the next day in class. So we're going to page 17. So page 17 looks like this. We're going to go all the way down right here to skill 2, because skill 2 says solving half-life problems. So basically what this is it goes through, and I'm going to give you some examples, but it helps to kind of figure out. So let's kind of read through. It says radioactive isotopes are unstable, which means that they spontaneously or readily decay into different isotopes or elements. Radioactive isotopes give off radiation in the process of radioactive decay. Radiation can be in the form of particles, that's probably important, alpha, beta, or positron, and or pure energy, which is your gamma rays. For radioactive isotopes, the rate or the speed of the radioactive decay is constant. All radioactive isotopes have a specific half-life, or time that it takes for exactly half of the sample to decay into something else and half the sample to remain unchanged. It is because of information about half-lives that we know how old the Earth is and how old fossils are. So it says we're going to do the following examples, and as your teacher shows you, each arrow represents one half-life, which will be important. I'm going to use arrows. I kind of want to pay attention over here. It gives me a little bit of info. So half-life is constant and can never be changed. That's important. The amount of a substance will never decay to zero. I can always cut an amount in half, no matter how tiny, so that's important. And each isotope has a specific decay mode, alpha, beta, etc., and half-life, which I find on table N, so that's important. So hopefully you have a table N right next to you and a calculator, and let's go through a couple problems. So if I go through problems that ask me basically time elapsed, they're going to be questions like number 1. So it says, how long will it take for 30 grams of Rn-222 to decay to 7.5 grams? So what I'm going to do is first, let's go to our table N and let's look up Rn-222. So I flip back. Rn-222. Here's Rn-222. It takes 3.823 days. It decays by alpha. So it takes 3.823 days to go through one half-life. And let's figure out, okay, well, I went from 30 to 7.5. So I go 30, draw an arrow, cut it in half. Now I have 15. Draw an arrow, cut it in half. Now I have 7.5. That's exactly what I wanted. So now let's count our arrows. I counted 1, 2. That means I went through 2 half-lives. So I go 3.823 days times 2, because I have to go through 2 of them, and I get my answer to be 7.646, and make sure I put my unit days. 7.646 days. If I did something like question 4, it says, how long will it take a sample, so how long, of francium-220 to decay to a quarter of its original amount? So I want to go back. They kind of give me the fraction remaining. So I actually want to kind of backtrack. Well, 1/4 is equal to, let's figure out how many halves. Well, is it just 1/2? No. So is it 1/2 times 1/2? 2 times 2 is 4? Yes. So 1/4 is the same as 1/2 times 1/2, which means essentially I did 2 half-lives. So I know from this quarter, 2 half-lives. So I'm going to go to my reference table, and I'm going to look up francium 220. Francium 220 has a half-life of, go to your table N, you should be looking at that right now. You should be telling me, Stu, it's 2.74 seconds. The S is seconds. And I went through 2 half-lives, so I'm going to take that 27.4 seconds times 2. And so to go through that, it's going to be 54.8 seconds. So they could ask me these problems in a little bit different ways, but essentially they're asking me how much time it took. Flip over to the next page. I'll do a different couple examples. So here, it's showing us our amount that is remaining. So let's do number 6. So it says how many grams of N16 will be left from a 16-gram sample after 21.6 seconds. So let's actually figure out what is the half-life. So we're going to go to table N, and I'm going to say, okay, from table N, I know it is 7.13 seconds to go through a half-life. I took a total of 21.6, so let's go 21.6 seconds divided by 7.13. What I'll get if I do that is 3. That 3 is telling me that I did 3 half-lives. So, how many grams would be left? Well, let's see. I started with 16 gram sample, so 16, cut it in half once. That's 8. Cut it in half again. That's 4. Ooh, I cut it in half twice. Cut it in half a third time. That's 2. That means 2 grams will be remaining of my sample. If I do a question like number 10. No, actually, let's do one more from this. So this one's a little, let's do 8. So it says, what amount of a 500-gram sample of iron 53 that will remain unchanged after 34.04 minutes? So I'm going to look up iron 53. Iron 53 is going to have a half-life of, let's say I would go to my table N, this is where I'm looking this up, would have a half-life of 8.51 minutes. But I went 34.04 minutes. So let's take that 34.04 and divide it by 8.51. If I do that, what do I get? I'm going to get 4. That 4 is telling me that's how many half-lives it's going to go through. So it's got to go through 4 half-lives. So I'm going to go back and say, okay, I can figure this out. I had 500 grams to start. So start by cutting in half. I get 250. Cut it in half again. I get 125. Cut it in half again. I get 62.5. Let's see, let's see how many arrows. 1, 2, 3. I gotta go one more time. So cut it in half again, and I get 31.25. This is an amount, so it's in grams. Again, I just count my arrows to make sure I went through 4 half-lives. If I do something that asks me about fraction remaining, let's do number 10. We just did problems very similar to this, but it says what fraction of a 100-gram sample of K42 will remain after 24.8 hours. So if I know it's K42, I'm going to say, well, I know its half-life. Its half-life is 12.36 hours. So it was 24.8 hours. So 24.8 divided by, well, let's put it here, divided by 12.36 is going to equal 2. That means it went through 2 half-lives. So if they tell me there was 100 grams, I don't really care because I want what fraction. So I just have to say, okay, well, 1/2 times 1/2 gives me 1/4. That's my answer. So you want to be careful. Sometimes they'll give you more information than you actually need in a problem. So I think you'd be able to do problems like this, so I'm going to keep going so I don't make this video too long. If they ask me about my number of half-lives, let's do a problem like number 15. So it says, how many half-life periods will it take for 50 grams of technetium-99 to decay to 6.25 grams? Well, I actually don't need to go to my reference table at all for this. I don't even care that it's technetium-99. What I care is I started with 50, and let's cut it in half until I get to 6.25. So half of 50 is 25, half of 25 is 12, half of 12, nope, sorry, 12.5, I can't do math. 12.5, I have a little decimal there, 12.5, and then 6.25. So I made it 6.25, 6.25, so I'm just going to count. I drew 1, 2, 3 arrows, so that means I went through 3 half-lives. And that's all they were asking me. So sometimes they'll just ask you, how many half-lives? Let's do an original mass problem. So, number 19. If 2 grams of an original sample of gold 198 remained after 13.45 days, what was the mass of the original sample? Well, let's go to table N. Let's look up gold 198. Gold 198 has a half-life of 2.695 days. So we went 13.5 days. So let's see, well, how many half-lives is that? So 13.45 divided by 2.695. That's going to give me 5. So this means I went through 5 half-lives during that time. And I have 2 grams left. I want the original. I got to go backwards. So I'm going to actually start over here and say, well, 2. Well, I'm going to draw my arrow just because I want to be consistent, but let's say I got to go back. So what number cut in half is 2? Well, it's 4. Okay, or I could just double it. And then I say, okay, well, all right, double 4. It's 8. Okay, double 8. It's 16. Okay, double 16. 32. Okay, double 32. 64. Double check that makes sense. 64 cut in half is 32. 32 cut in half is 16. 16 cut in half is 8. 8 cut in half is 4. 4 cut in half is 2. I went through 1, 2, 3, 4, 5 half-lives because 5 arrows. So 64 is my answer. Sometimes the original mass is tricky. You got to work backwards. All right, one more section. I want to do basically one more problem with you. So let's do number 22. So it says, an original sample of the radioisotope fluorine-21 has a mass of 80 milligrams. Only 20 milligrams of this original sample remain unchanged after 8.32 seconds. What is the half-life? So they want to know, well, how long is it then? So, okay, I went from 80 to 20, so 80 cut it in half would be actually 40, so cut that in half, it would be 20. So I went through 2 half-lives. So 2 half-lives happened in 8.32 seconds. So go 8.32 divided by 2, and you're going to get 4.16 seconds would be an individual half-life. Let's do one more problem. 24. what is the half-life of a radioisotope if 116 remains undecayed after 26.4 days? So let's think. I can figure out 116. All I'm going to do is say, okay, I have 116. Well, is that equal to 1/2? No. Is it 1/2 times 1/2? No, that'd be 1/4. Is it 1/2 times 1/2 times 1/2? No, 1/8. Is it 1/2 times 1/2 times 1/2 times 1/2? Yep. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. So then I just count. I did 1, 2, 3, 4 halves. So that means it's 4 half-lives. And so I'm going to say, okay, let's just take that 26.4. Let's divide it by 4. And I'm going to get 6.6. And my unit would be days. Days. So I hope you can see that half-life sometimes is a little tricky. There's not specific notes I can give you. We just have to figure it out. We're going to do more practice in class tomorrow. Try to re-look over these examples that I just did. That will help you kind of solidify it in your mind. And we'll do some more practice tomorrow. Thanks for watching, guys. See you soon.